to hopefully record this and post this in the slides. So if anybody wants to see any more details, it should be online. And of course, feel free to email me. This is work that I've done over the years with various collections of students. If you went to Professor Clary's talk yesterday, a lot of the background information is going to be similar, but since everybody has not gone, I will try to go through it somewhat quickly. So I want to talk a little bit about what is Benford's law. So the motivating question is you have some collection of data and you want to know how often is the first digit 1, how often is it 2, 3, 4, et cetera, et cetera, et cetera. For some things, the data might be clustered. So I noticed a friend of mine who's a big Red Sox fan. If you look at batting averages, you will not expect to see many first digits of 1 in Major League Baseball. If you're batting below 200, we have something for you called the minor leagues or retirement. If you're batting $1,000, you must be a pitcher with 1 at bat, something like that. Most batting averages will start with a 2 or 3. You're not going to expect some kind of distribution hitting all the digits. But for a lot of things, spanning several orders of magnitude, you might expect maybe 10% of the time I'm 1, 10% of the time I'm 2, so on and so on and so on. And then you realize, well, my leading digit's not going to be a 0, so you correct to maybe 1/9, or about 11%. But it turns out for many distributions, that's not what happens. It's actually more like around 30% of the time you have a first digit of 1, and only about 4.6% of the time do you have a first digit of 9. You can see this in a variety of different data sets, the Fibonacci numbers, Twitter users by the number of followers, most common iPhone passcodes, please don't ask how I got the data, distances of stars from Earth, those were painful measurements to do. No. So a lot of these data is very easily available online. And the general phenomenon is the more things you average over, the closer to Benford's law you seem to get. Fibonacci numbers are beautiful. That would be several topics in itself. And so we say a data set satisfies Benford's law if, in the limit, we basically have these probabilities. So I want to give you a sense of where does Benford's law come from? What kind of processes can we study and show that Benford's law happens? What kind of open problems are there for people who want to try to look at some problems in these fields? And so depending on how much time there is, that'll determine how much of the nitty-gritty details we actually get into. Just for some fun, how many people have heard of the 3x plus 1 problem? So I do have a paper on that showing that in some sense it is satisfying Benford's law. At least once in your life, if you do number theory, you should bang your head on the 3x plus 1 problem and then move on if you want to become tenured to work on something else. But it's amazing how many different places Benford's law shows up. It shows up in a lot of financial fraud or election fraud to try to determine if a data set has been manipulated. And when I am not recording this, I'm happy to talk to you about some of the work I've done with colleagues about trying to detect when fraud has happened or when fraud has not happened. Okay, just a little bit of background material so we're all on the same page. Modular, we say A equals B mod C. If A minus B is an integer times C, basically this is just the clock arithmetic. Normally we will look at clocks with just 1 hour. So we'll look at are 2 numbers the same up to an integer. The significand is I can write any number in scientific notation. So base 10, the significand will be a number between 1 and 10, and then I have some number of powers of 10. If I only care about the leading digits, I don't really care about that 10 to the k. I only care about the significand. Well, the problem is most of the time you can't just chop off the 10 to the k when you're applying functions. You have to apply your function to the entire number. Now, the mantissa is the log of the significand, and that's going to give me something that's going to live between 0 and 1. 2 numbers have the same leading digits if and only if A and B, if and only if they have the same significand. And now what's nice is if you take the logarithms and look at what you have over there, then you see that the logs will differ by an integer k. So another way of saying that they have the same leading digits is their mantissas are the same, or the log of their significance differ by an integer. The key observation is that, as I said, they have the same log mod 1 if and only if they have the same leading digit. This actually suggests a tool that will be very useful for proving results about Benford's law for analysis. So if I give you the function e to the 2 pi I u, I can chop off the integer part of u without changing anything there. So I take the logarithm of my number, I use trig functions, and then I can do my analysis, and everything works out beautifully. So we say something is strong Benford if we care about more than just the first digit. Maybe I care about the entire significand. And so it turns out that something is strong Benford if and only if its mantissas are uniformly distributed in 0, 1. And we'll talk a little bit more about why this is true and how we can use this to prove some things. So just to make sure we're all on the same page, to be equidistributed or evenly distributed or uniformly distributed just means if I have a sequence and I want to know how often does it land in subinterval AB, I count how many occurrences in the first n terms, I divide by the number n, and that should converge to B minus A. So to prove certain things are equidistributed, if you can show that I can write myself as n times beta mod 1, it's a beautiful theorem that if beta is irrational, then n beta mod 1 is going to be equidistributed. So if I have an exponential process, say alpha to the n, when I take a logarithm, I'm going to get n log alpha. And if log alpha is irrational, then this is going to be equidistributed. So the original geometric process will be Benford. And this is the stock market example that my colleague Rick talked about yesterday. Okay, so because I had to choose the examples ahead of time, I chose one of my favorite examples, the square root of pi, in honor of now being not quite pi day, so I don't want to do exactly pi. So what's nice about this is if I look at this mod 1 for the first 10 values, it's not perfect. You'd be a little bit suspicious if I gave you something that was perfect, but it's close to perfect, so not so bad. As I look at now the first 100, you can see it's pretty close. If I look at the first 1,000, it's even closer. If you look at the first 10,000, if you have really good eyesight, you can see small little fluctuations. And it's a big question about how quickly does it converge to equidistributed? What kind of information about the structure of the number leads to different rates? And so the fundamental equivalence is that if I give you a sequence xi, it's Benford if and only if its logarithms mod 1 are equidistributed. Let me just show you why this is true. And so over here, I have my significance going from 1 to 10, and then down below, I have the logarithms. And if you look at it, what numbers will have a first digit of 1? Well, the log of 1 is 0. The log of 2 is about 0.3. And so if I'm equidistributed down below, that's actually 30% when I exponentiate back upward. And this is where the digit bias is coming from. There's really no digit bias if you look at your numbers on a log scale. Now, if you look at numbers on a log scale, most things, we're not going to take logs of batting averages or logs of temperatures. And so when we look at the numbers as they come in, we will see this digit bias. But if you look at it on a log scale, it's all gone. Rick talked a little bit about how this is a great example for probability, basic properties of the logarithms, so that if you put these all together, it does give you a probability distribution. A lot of it, as I said, comes down to finding the right perspective to look at things. So I love to do Rubik's Cubes. The one on the left is the standard Rubik's Cube. The one on the right looks a little bit strange. Its sides are actually 2 by 3. They're really essentially the same Rubik's Cube if you look at them the right way. It's actually, the side is cutting across the colors. And if you hold it at a 30-degree angle, it's the same algorithm to solve. And so much of these problems comes down to, can you find the right way to look at things? And the right way to look at things is to look at it on the log scale, look at the log scale mod 1. All right, so what I want to do, I want to make sure I do at least one proof. So I'm going to skip over the new stuff I've done with students and go to some stuff I had done in previous years on stick decompositions. And so consider a stick of length L. And then what we're going to do is we're going to choose a fixed probability P. You could, of course, choose a different P every single time. But for simplicity, let's just use one probability every single time. And I'm going to split the stick at P. And then I'll have 2 sticks. And I'll split each one of those at P%, and I'll keep iterating. And then we can ask, what's the distribution of stick lengths? I realize it is before 11 o'clock in the morning. Can anybody tell me any P's where they don't think the stick fragments will be Benford? Any probability where, if you look at the collection of all stick lengths, I don't expect Benford? There's 3 answers. 1, 0, that's 2 of the answers. There's one other example. 1/2, because if I take 1/2, everything is the same length. So the conjecture is that if we keep doing this and we keep breaking into more and more pieces, as long as we stay away from 0, 1, and 1/2, it should be Benford. And so we did a bunch of experiments. Here's 0.51. It's really close to 1/2, but here's 0.99, really close to 1, and it looks Benford. We then took P equals 1/11, and it is not Benford. Now, what's interesting about 1/11 is 1 minus P is 10/11. Now, why is that interesting? Well, let's look at what's going on. And again, it all comes down to trying to find the right perspective to look at things. At the nth level, we have 2 to the n sticks. And normally we would write the n plus 1 distinct lengths as P to the n minus j, 1 minus P to the j. But if I write it in a better way, let me pull out the p to the n, and then I've got 1 minus p over p to the j. So what I see is of my stick lengths, I change by a multiplicative factor from one to the next. Imagine 1 minus p over p was 10 to a power. Well, then all the sticks would have the same digit, the same leading digits. Or maybe 1 minus p over p is not 10 to a power. Maybe it's 10 to the 1/2 or 10 to the 2/3. So then if I do it 3 times, I would then get 10 squared. So if 1 minus p over p is 10 to a rational number, I don't get Benford. And so that's what I'm going to show you, just so we have at least one proof in the talk, that if 1 minus p over p is 10 to a rational, then we do not get Benford's law. And so to prove this, there's a couple of ways you can do this. What you can do is you can say, well, if 1 minus p over p is 10 to the r over q, where r and q are integers, then every time I increase by q, I just multiply by a number by 10 to the r. So if I want to look at what fraction of my numbers have the same leading digit, well, every time I increase j by q, they're going to have the same leading digit. So I just have a sum of binomial coefficients. If you know a lot of identities, it turns out you can relate this to sums of products of cosine functions, which I'm sure everybody remembers from their trig days. Or what you could notice is, if I just shift j's congruence class by 1 or 2 or 3, these sums are basically the same. You can dominate by taking away the first and the last term. So they all have to be approximately 1 over q. So it has to be uniformly distributed. So that's the faster way of going through. If I take p equals 3/11, the log base 10 of 8/3 is irrational. And you see it's not so badly approximated by Benford. If I take p equals 1/11, which I mentioned before, that number was not chosen accidentally. You can see it's very non-Benford. And then having some fun, the 1 over 1 plus 10 to the 33 tenths, this gives you a very non-Benford distribution. So in the last 3 minutes, the problem we looked at was a generalization of another problem I did with my students, where we take the stick and we keep breaking it, but we only continue to break if the stick length has a certain remainder mod a given number. So maybe I want to look at things mod 12, and I will only continue to break sticks if the length is not congruent to 1, 2, 5, or 7. And we wanted to know, how do these different cut endpoints affect the distribution? And so, obviously, if I say every value I'm going to stop at, then I only do one process. Or if I say I never stop, I'm going to keep going. Or if I only stop if it's congruent to 1, then it's going to be many more pieces coming in. And so just quickly going through our results. Whoops. I'm trying to hit the little circle. It's not letting me hit the little circle. We'll go warp speed. It's not letting me hit the little circle. All right. So we then looked at what happens, and we found a truly fascinating behavior. We get Benford's law if the number of stopping residues is exactly half the possibility. If it's not exactly half, it's not Benford. And so I could go through and I could talk about the proof. And given that I have about 2 minutes left, I don't think that's a good idea. So instead, I'm going to do proof by picture. So here is a picture. And we are looking at stopping at only the odd lengths. Well, that's, half the values are going to be odd. So that looks, pretty promising in terms of that looks uniformly distributed. Here, we're only stopping at 1 mod 3. So we're only stopping for 1/3 of the lengths. And you can see highly non-uniformly distributed. Here we're now stopping at 0 or 1 mod 3. So again, not stopping at half the time, stopping at 2/3. Again, very non-uniform. And here we're stopping at 1 or 2 mod 4. So not just all the evens or the odds. It doesn't seem to matter at all which residue classes you choose. As long as it's exactly half the residue classes, you will get Benford behavior. And so the proof is to basically take this very discrete process and approximate it by a continuous process where we can use very nice techniques. The last thing I just want to remark on is there are a lot of open problems on this. We were doing things based on residue classes. There are other things you can do. You can try to break it up into, is it an integer that is a prime? Is it a square? How do properties of those numbers? We heard talks about powerful numbers and power-filled numbers and all that stuff, and powdered numbers. You could play all sorts of games like this in terms of what it decomposes into. This is inspired by a lot of problems in physics in terms of you have a nucleus, which is decomposing, when is it going to stop? What are this, natural stopping points? And speaking of natural stopping points, I think I have reached one, so I will end here. Okay.